Sorry. Sure.
Good morning, everyone. Welcome to Cardiology Rounds. It's my pleasure this morning to introduce one of our C3s in cardiology, Dr. Pascal Theriault-Lauzier. He's going to be talking today on artificial intelligence in cardiac imaging. He's completing his third year in cardiology at the Heart Institute, and then he'll be proceeding with an interventional fellowship with a year here, and then going on to Stanford for a year. So we welcome him this morning and look forward to his presentation.
Well, thank you very much for the introduction. It's a pleasure to be presenting today. Here's some of my disclosures. So a black box is a system which can be viewed in terms of its input and outputs without any knowledge of its internal workings. And in many senses, artificial intelligence really can be seen as a black box, either because of the algorithm themselves not being very transparent on how they come up with predictions, and also because of the entire field of artificial intelligence, also always being, marred with a lot of terminology. Despite this, the interest in artificial intelligence has been growing over the last decade, and we can see in the last year alone, almost 1,000 articles have been published on the topic of artificial intelligence in cardiac imaging. So the objective of this presentation will be to introduce some basic concepts in AI. We'll review some of the applications of AI in cardiac imaging, present some of the work that's been done at the Heart Institute, and discuss some ethical implications and challenges of AI. So let's start with basic concepts. So we're all familiar with classical computer programs that take in rules in the form of computer code and data that can be coming from sensors and produce answers. Now, the idea of machine learning kind of flips this relationship on its head. So a machine learning algorithm will take in data and associated answers and produce as its output rules that link these two concepts. So we can take a very simple example. Say we wanted to predict LVEF, so the ejection fraction, from a patient's ECG. So we could, write down a rule that relates the QRS duration to the ejection fraction and feed this into a classical computer program to produce a prediction. Of course, we don't have a formula like this. I just made this formula up myself. But what we do have is a lot of data. So we have a lot of patients, ECG data and their ejection fraction data. So what we can do is feed this into a machine learning algorithm and create a rule for the ejection fraction. So a very simple example of this would be a linear regression. Really, nothing very fancy here. So if we plot EF versus QRS width, we can draw a line through this data. And then once we're faced with a QRS duration that was not in our training data, then we can use this rule. This process is called inference. Using a model on previously unseen data, and we could predict an approximate ejection fraction based on this. Now, what we've done here is nothing very complicated, but we've basically built a basic building block, in a sense, an artificial neuron, you could say, that takes in a certain data point, in this case, the QRS width, multiplies it by a constant, adds a certain intercept term, and produces an estimate of the ejection fraction combining this data. Of course, we can make this a bit more complex. Our neuron can take two different inputs, each multiplied by their own weight, and combine with an intercept to produce our prediction. So of course, that's when more data is available, that's when really the value of machine learning becomes more obvious. So of course, in this a contrived example, you could add many more ECG concepts to your database and use those to try and predict ejection fraction. So for example, here we have the Q wave, left bundle morphology, QRS axis, and so on and so forth. What we could do is define higher level concepts, such as ischemia, with the presence of Q wave, hypertrophy, that may taking the QRS axis, QRS amplitude, whether there's conduction disease with the QRS width or the presence of left bundle morphology, and the P wave amplitude for left atrial enlargement. And then as a second step, take these higher level concepts, combine them to predict ejection fraction. Of course, in the field of machine learning, we don't have to define these connections to be limited. So we can create fully connected connections between our artificial neurons, and we don't have to define these concepts for the artificial neuron, we can let the machine learning algorithm discover these concepts on its own. So this, in the terminology of machine learning, is called a fully connected layer. And of course, I'm speaking of layers. We can add several layers to a neural network. Again, just in terms of terminology, these would be called features. For example, the Q wave axis, the left bundle morphology, these are features. We have hidden layers that are part of the neural network, and then an output layer that gives us our predicted ejection fraction in this case. Now, if we want to go a step even further, instead of feeding in the data of the ECG that has been extracted from the signal, we can feed the signal itself into our neural network. And of course, this would lead to more feature complexity. So we would need to have a lot more input nodes into our neural network. The model will need to be much more complex to take in that kind of data. We'd have to have a lot more examples, samples of data to train the neural network, and this would take a lot more time to train the neural network. This really brings us to the main difference between classical machine learning and deep learning. So classical machine learning uses human design features, in our example, Q waves, QRS axis, and so on and so forth, while deep learning uses automatic feature extraction. So we would, feed in the raw signal and then let the model decide on those features. You've probably seen this type of a graph before, showing the relationship between artificial intelligence, machine learning, and deep learning. And again, to reiterate, machine learning algorithm, that's what it states, they use human extracted features from data and improve with experience. Now, deep learning, neural network algorithms that learn the important features in data by themselves. So that's really the crucial differentiation between those two concepts. Of course, this was an example with an ECG, but we can use it with images. And we give an example of a regression model that predicted ejection fraction, but you can have many other tasks that can be applied. For example, a classification model could be detecting if a certain disease process is present or not. You could have a detection model that tells us within an image if there is a certain feature that is present or not, and the localization within the image. And then we could use a segmentation model that takes in an image and then outputs a pixel, wide analysis of the image and tells us which parts of the image, which pixels are part of that region of interest. Now, a lot of the development that has been made in the field of AI over the last decade really revolves around convolutional neural network. And to explain some of these basic concepts, I'm just going to take a very simple example. Here we have a circle, the image of a circle. And if we shine a flashlight on this image, but instead of just shining a beam of light, we shine a certain pattern on top of our image. And then we measure mathematically how similar this pattern is to our underlying image. And we store this into a new image. This process is exactly what a convolution is. This pattern that we're shining is called a kernel. So this is really quite a simple process that we can apply. Now, how does this help us in the field of machine learning? Well, you can make neural networks that are convolutions of convolutions. So these are some of the examples with convolution kernels at the very beginning of the network. You can see it they take in lines, for example, color patterns, and so on and so forth. And as we go deeper into the neural network, we get features that are much higher level. For example, spokes of a wheel, a flower, and things like that. So we can really take in much more complex features as we go deeper. Now, how does this help us to actually create a prediction? Well, let's take an example with an input image. We can apply convolutions onto this image with several different kernels. Then we apply convolutions on these convolutions, going deeper and deeper into the model. And these are called feature maps. Eventually, we feed the results of this into a fully connected neural network, as we discussed earlier in the presentation. And the outputs of this, we output essentially a prediction, a statistical prediction of what object is in our input image. So this is really the feature extraction process that happens in a convolutional neural network. We have a classifier at the end and then our probabilistic distribution. So how is this used in cardiac image analysis? Well, we'll review 4 different studies, of course, to just give an appreciation of some of these applications in different modalities. So let's start with echocardiography. In this study by Zhang and al., published in 2018, they used their goal was to produce a fully automated echocardiogram interpretation system. So they used 14,000 echo studies that they fed into their system. The first test that they studied was view identification. And as you read articles on machine learning, you may come across these types of tables. So these are called confusion matrices. So on the vertical axis, you have the ground truth. In this case, different echo views, and then the prediction, the associated prediction. It's very similar to a 2x2 table you may have come across before. So any entries that are not on the diagonal are essentially errors or misclassification. So in their case, they reach an 84% accuracy for classification in this study. They also studied chamber segmentation. So in this case, they used 5 different standard views. They had highlighted and selected different regions of the image corresponding to different structures, and they let the algorithm learn how to identify these structures. And they reach quite a high accuracy at 64.6 to 89.6% accuracy. They use this segmentation algorithm then to predict ejection fraction and to measure ejection fraction. They reach a 6% mean absolute deviation for the ejection fraction, and they did observe a tendency to overestimate chamber size. They also studied the identification of certain disease processes. So for hypertrophic cardiomyopathy, for example, they did the ROC analysis and found an area under the curve of 0.93 for their model. So quite successful. For amyloid detection, they reach 0.87, and for pulmonary arterial hypertension, they reach 0.85. So quite impressive results. So moving on to nuclear cardiology. So the goal of most nuclear cardiology scans is to identify ischemia, and often you want to identify ischemia based on the territory and on the patient level. So in this study by Betancourt and al., published in 2018, they used the polar maps of the patient using SPECT, as well as a quantitative map based on a TDP, which is just it's called a total perfusion deficit. It's a voxel-based ischemia quantification score. And they fed that into a deep learning model, a convolutional neural network, very similar to what we discussed earlier in the presentation. And then they had some fully connected layers for classification, and then they produced a probability of obstructive coronary disease more than 70% stenosis in all territories, as well as the patient level. So they used just over 1,600 patients to train this algorithm, and they compared it to the per patient TDP, which is a method of identifying ischemia at the patient level that is not based on machine learning. And they did show a significant improvement in performance using a deep learning method that used the raw and TDP data. Interestingly, there was no improvement when they used only the raw data. So that is quite interesting. And also the improvement in accuracy is relatively small in this case. They also showed the same type of improvement at the per vessel basis. Now they extended this study and they looked at outcomes. So they tried to predict MACE in a group of patients, just over 2,500 patients. And in this case, they used a classic machine learning model using patient characteristics as their input, as well as imaging data that had been extracted from images. And in this case, they did show a significantly better performance when they combine machine learning, algorithm using clinical data and imaging data. So this has been done at the Heart Institute as well, and by the group of Dr. DeCamp. So they, of course, they studied PET MPI in this case with myocardial blood flow studies. They used 7,500 rest and stress scans. In this case, the data was 3 vascular territories and 17 segment data. And the task that they looked at is the localization of coronary artery disease and the detection. So the detection was on a per patient basis, and they studied a series of different algorithms to do this. So they use a linear regression that is not typically seen as a machine learning algorithm in the modern sense of the term, and they used a UNet, which is a convolutional neural network, and a random forest. So interestingly, they showed a significantly better performance with machine learning approaches for detection on a per patient level. However, for the localization per vessel, they showed really equivalent performance in this case. So interesting results that were published earlier this year. Now moving on to cardiac MRI. So a classic task in MRI is to segment the heart, the left ventricular cavity, the myocardium, the right ventricle. And if you've ever read an MRI scan, you'll know that these tasks can be quite long and tedious to perform. So this is an obvious application for AI algorithms. And in 2017, there was this competition that was launched by McKay. It was titled the Automated Cardiac Diagnosis Challenge. And the task that was, proposed was to segment the left ventricle, the RV, the myocardium, and to classify 150 patients into 5 different groups based on the disease, entities that the patient had. Several groups were allowed to submit algorithms, and they were compared head to head amongst each other. So here's some of the groups that's propose some algorithm for segmentation, and some of the groups that propose algorithms for classification tasks. So that most of these, the vast majority of them are based on convolutional neural network, or CNN, and a lot of the classification algorithms are based on random forest or support vector machine algorithms. Interestingly, the results were very impressive. So they showed very high correlation with the labeled images. And for example, for LVEF, they showed a mean, absolute error for the LVEF. The best that was performed was 2.1% error, and this led the authors of the challenge to conclude that results presented thus far suggest that we are on the eve of cracking the nut of fully automated CMR analysis. So this was published in the IEEE Transaction Medical Imaging 2018. Now moving on to cardiac CT. So as we know, FFR is a very powerful method to do functional testing in the cath lab on a coronary lesion. And interestingly, you can use cardiac CT to estimate FFR based on a model of the vessel that is extracted from CT images. And then you use a computational flow dynamics analysis to see how much pressure is lost across a stenosis. And then in the Discover Flow study that was published in 2011, there was a demonstrated significant improvement in the ROC analysis for these using CT FFR. And now the limitation of this method is it needs to be done in a centralized, fashion, so by the company on their own premises, because the complexity of this analysis. Now, some researchers from Siemens proposed this simplified method where several characteristics of coronary vessels are automatically extracted, and these features are fed into a neural network in order to predict CT-FFR in these patients. Interestingly, they showed a very high correlation or similar correlation for the CT-FFR measured with flow dynamics algorithm or using a machine learning algorithm. So very similar performance in this case. And this interestingly led to an 80-fold improvement in computational efficiency with the machine learning approach. So very impressive improvement. Now, of course, we've only scratched the surface of this topic. So if you're interested in learning more, we just published this review in the Canadian Journal of Cardiology. So I'll let you read it at your own leisure. You may be interested to know, so how far is AI from being applied in the clinic? Well, interestingly, the FDA keeps a database of AI and machine learning enabled devices. They're currently approved, and there's 44 currently approved in cardiology and cardiac imaging application. And some of them are currently used at the Heart Institute. For example, Circle CVI is used for MRI analysis and does have an approval from the FDA for their AI algorithms. Now let's move on to some of the research that we've done at the Heart Institute. So as we know, cardiac implanted electronic devices are widely used, and they're used for a wide array of indications. Interestingly, the rapid device interrogation can be life-saving, and unfortunately, the interrogators between the different manufacturers are not mutually compatible. So it's often important to identify the device type in an emergency. So one way that this can be done is using a chest radiograph, as we see here. So as we know, the imprinted circuit, the electronics of the device are quite well seen on a chest radiograph, as you can see here. This led Jacob et al. In 2011 to propose an algorithm that allowed a human to identify, a cardiac implanted device, and this really involved the comparison of the device to aviator sunglasses or a glass of wine or bird, or something that was approachable for a human. And they compared different specialists based on their specialty between internal medicine, cardiology, emergency medicine, anesthesiology, as well as a non-cardiologist. So they saw an error level that reached up to 8% for pacemakers with their techniques. So of course, this has been also studied for cardiac implanted devices using a neural network. So in this small study, they used 1,600 images, chest X-ray images, to train the neural network, and they compared the accuracy of cardiologists and electrophysiologists, and showed that the neural network actually outperforms cardiologists and electrophysiologists for the identification of the manufacturer of the device. Of course, there were some limitation to this study. So one part of the study is they grouped devices in device groups that were a bit arbitrary, and they didn't clearly describe how they did this. They only mentioned that during the extraction, in several cases, a manufacturer introduced a new model. There's no detectable change on the radiograph. So they did this manually. That's our best understanding. There's an app that's available for this. Unfortunately, has mixed reviews on the App Store from Google and Apple. And I tried it just to give you an example. I took a picture of my coffee mug yesterday, and it assured me with 100% certainty that this was a Medtronic device. So definitely not quite an accurate estimate. But without being flippant, this really highlights the role of humans in the interaction with AI algorithms. We want to always make sure the prediction that it's providing us are accurate, and that data we're feeding in is also appropriate. So some of the questions we had, so we wanted to evaluate if a neural network can detect a device automatically on a chest X-ray image. We wanted to see if a neural network could quantify the quality of the image to say if it was good enough to give a prediction. We wanted to study this type of classification model on a multi-institutional scale database of devices, and we wanted to see if neural networks could provide some insight into which devices are really identical under X-ray imaging. So here's some of the data that we extracted. So we obtained approval both from the MUHC in Montreal at McGill and from the Heart Institute to directly pull data from the PACS server. And we used an automated script to pull these images, and those are available on GitHub. So we extracted at both institutions from 21,700 patients. We extracted 266,000 chest radiographs directly from the PACS system, and this covered 531 different models of cardiac devices. So this is just showing all the different cardiac implanted devices model on the x-axis, and on the y-axis you have the number of chest radiographs for each patient. It's a logarithmic scale, so you can see certain devices we have more than 10,000 examples of, while some of them we have only one example. What we then proceeded to manually segment the device, so manually draw a box around each device. And I'm very thankful for Daniel Garcia, the MUHC, and Willie Wang at the Heart Institute who helped us with this process. We then quantified the quality of images going from 0 to 4 on the 5-point scale. And on the level 4, we could really clearly see the circuitry, and at level 0, there was no device visible. And then we apply machine learning algorithm to this data. We studied 3 different tasks: object detection, quality classification, and then device manufacturer type and model classification. So starting with object detection, we use the TensorFlow object detection API to train a model, and we use only image quality 3 and 4, and we had a training set in this case of 14,000 images and a validation set of 6,000 images for this task. We obtained quite a high accuracy at an intersection over union of 0.5. We had 99% accuracy in our study. Interestingly, we applied the algorithm to the entire database at the Heart Institute afterwards and detected 51 patients that had more than one device implanted. And we provided this data to Dr. Aiden and Dr. Wang, who then did a cohort study in these patients. And they studied outcomes such as the abandoned device infections, whether the device was explanted, and so on and so forth. And this study was just submitted for review. So stay tuned for the results in the future. Interestingly, the algorithms also detected some device incorrectly. For example, an LVAD here was detected as an implanted device or a prosthetic shoulder. And so some of the other examples we found, the magnet that's applied on top of the device, or a calcified breast implant, LVADs, prosthetic shoulders, for example, were inappropriately detected. So we used some of these inappropriately detected images to quantify quality, and we use them in the 0 level quality where no device is present. So we use 50% images that were inappropriately detected of non-cardiac devices, and 50% of them that were from the contralateral side of the chest radiograph, so that it would have a similar underlying anatomical features. And then the other, the other quality levels were drawn from our labeled data. So we trained 3 different algorithms for this and reached an accuracy level between 84 and 86%. Even larger size models did not provide a very significant improvement in performance despite their much larger size. These are some of the results. So this is our confusion matrix. Again, the true image quality on the x-axis and the predicted image quality on the y-axis. And we can see that most of the errors that we see are between adjacent levels of quality. So this, given the subjective nature of image quality, we were quite happy with those results. So we reached an 85% accuracy. So then we moved on to device manufacturer and type classification. So again, we combined our database between McGill and the Heart Institute, manual label 30,000 images, and then fed this into our quality class model and our detection model to obtain a clean database of 103,000 images, and these only had quality level 3 and 4. And then we manually, monitored this database to make sure there was no errors that were made. Then we trained an algorithm to identify the manufacturers among 7 different manufacturers of devices and 5 different types of devices, including pacemakers, ICDs, CRT devices, subcutaneous ICDs. Our training set, in this case, at 21,000 images and a test set of 9,000 images. And we reached an accuracy level on our validation set of 99.3% accuracy. Now, you may wonder, how do we know that the algorithm is really looking at the correct part of the image? Well, we can use a special type of algorithm called a GradCam algorithm. And the way I think of this is almost like an eye tracking algorithm for the neural network. So it allows to see which part of the input image actually contributes to the prediction that the model is making. We can see, for example, for CRTP devices, it really focuses on the connectors. And with CRTP devices, we know we have 3 separate connectors in this case, so it makes sense that it would look at that part of the image. So this is one of the techniques that are used to open the black box again of neural networks and provide some insight into why certain predictions are being made. Now we moved on even one more level, and we looked at, for specific models of devices, can we identify the specific models? So we look, for example, only for Medtronic pacemakers, we have 77 different models in our database, and that covers over 45,000 images only for Medtronic pacemakers. And of course, we expect several of these models to have very similar appearance on their chest radiograph. So we trained the model to try to predict this, and we reached an accuracy of 77%. So not a perfect accuracy, but we expected this. And then we used the errors that were made, so the off-axis data that we see in our graph, to see which devices are actually very similar between each other. And we use a hierarchical clustering algorithm to do that. And these are several of the clusters that were identified. For example, the light blue sign cluster here, despite the devices having a very different name, their appearance on their chest radiograph is extremely similar. And they're all dual chamber devices. You see 2 connectors in this case. In the red cluster, we have single lead devices in this case. And despite the devices have, again, very different names, they're all very, very similar under X-ray imaging. Of course, we can move even one step further and devise a mobile app based on this. We designed and implemented an app using the Ionic framework and the TensorFlow.js machine learning framework. And here's a kind of tour through some of these slides you've already seen, but through the viewfinder of the app. And you can see there's markers on the viewfinder that are white, and these viewfinders indicate whether the quality of the image is good enough to provide a prediction. So you can see as long as they're white, there's no device detected, as you can see, and there's some image quality feedback that has been given. And as soon as a device is detected, the viewfinder turns green, and then the prediction is outputted. And this is being done live multiple times per second on my cell phone, so it gets updated live. And then we can, of course, use it on several types of different devices. This is a Medtronic ICD, for example, and it's quite certain of that. This is a Biotronic ICD, and so on and so forth. So this relieves this issue with the coffee cup I was showing you earlier. So what we've done is, again, to summarize, created a large database of chest radiographs and patient with cardiac implanted devices. We applied state-of-the-art convolutional neural network for object detection and classification, and we developed a point-of-care app to deploy these models and make them available to clinicians. So, of course, to conduct machine learning and deep learning research, we need to have a computing infrastructure to be able to do that successfully at scale. And really, this is a slide from the Google Developer Machine Learning Crash Course, but it really showed the amount of time and the number of tasks that you need to perform in the machine learning project in order to take an idea from the bench all the way to a product. And really, the machine learning aspect that we spoke about during the presentation is really only a small part of the entire life cycle of a device. So in order to facilitate some of this, the Heart Institute, had the vision to invest in a shared computing facility called a high-performance computing cluster. And what this allows is to have a network drive that stores the data locally and securely, and then shares it to high-performance compute nodes that can then be shared between different research groups. And this is secure, so the given research group does not have access to the data of a different research group. And currently we have one compute node that is operational, and the Heart Institute has just purchased 2 more that have just arrived and are being installed. I'm very thankful for the group at the Heart Institute, Timothy Zakutny, André Lecuyer, Richard Clark, Richard Lefebvre, Bahar Taji, and Christine Harvey, who've been very helpful in the deployment of this cluster at the Heart Institute. And I want to mention Bahar. She's a recent hire at the Heart Institute. She's an AI engineer and will provide a lot of the support for the computing cluster, as well as support for AI projects at the Heart Institute. So the cluster uses Slurm, which is a software that's used on 60% of the top 500 supercomputers in the world, and it allows researchers to request exactly the amount of resources they need for their project, and really to share this resource amongst different researchers very easily. And of course, different researchers will have different requirements in terms of the machine learning framework they want to be using. And there's, a very high number that keeps growing, some of which are TensorFlow that we've used that's supported by Google, but PyTorch is supported by Facebook, for example, and some of them are independent. So we use a container type environment that allows researchers to use any library they want and run it on the cluster from a completely transparent manner. So this allowed us to contribute with MITRE, which is a nonprofit U.S. research organization, very large with over 8,000 employees. They do a lot of their work with the U.S. government in aviation, defense, healthcare, and homeland security. And they've been collaborating in the Heart Institute on several AI and data science projects. I've had the pleasure to collaborate with them on a project with Dr. Misika on aortic valve calcification, and it's been really a pleasure working with them. I don't have yet any data to share with you, but keep posted over the next several months on this. So I just wanted to touch base finally on some of the ethics and challenges with AI algorithms. This was an article published in The Atlantic titled "AI-Driven Dermatology Could Leave Dark-Skinned Patients Behind." So this was, kind of noting an issue, in particular in the field of dermatology, where AI algorithms have been used to identify skin lesions, and they were trained on data from Germany in patients with very fair skin, and the algorithms did not perform well on patients with darker skin tones. So this was a quote from the article: "If you don't teach the algorithm with a diverse set of images, then that algorithm won't work out in the public that is diverse." So this is an example of bias in the field of AI. And this is a recent tweet by Gary Collins, who's a statistics reporter or a reviewer for the BMJ, and I'm thankful of Dr. Hibbert for pointing this tweet to me. He notes, "Seeing more reviews looking at reporting and consequences of poor reporting on risk of bias of machine learning and AI in clinical prediction models." And they're preparing a guidance document on this. So you can see a lot of articles recently published highlighting the risk of bias in studies on prediction models developed using supervised machine learning techniques. So the very effervescent field currently. And the reason why there's so much controversy, I think, is in part because there's two worlds that are colliding: the world of statistics and epidemiology, and for decades have been producing prediction models and have developed very robust ways of validating these models, and the field of computer science and data science that's been emerging over the last decade and comes from a very different and takes a very different approach. And this is a quote from this article, saying, although there is a clear overlap, different approaches to model development, validation, and updating have appeared, and different and sometimes conflicting terminology has arisen. So based on this, there's been protocols that have been developed for reporting of AI algorithm for diagnostic and prognostic prediction models. So this will be, I believe, in the future, something required for any AI-based research study to be published. The WHO also in the last year has released ethics and governance of artificial intelligence for health. So it's a WHO guidance document, and they highlighted 6 different ethical principles that are crucial when talking about AI research, but also AI deployment and use in the clinic. So number 1 was protecting human autonomy. So humans should remain in control of the AI algorithm, promoting human well-being and safety in the public interest. So AI technologies should not harm people, of course. Ensuring transparency, explainability, and intelligibility of algorithm. So AI technology should be intelligible and understandable. So you shouldn't be just getting a prediction and you don't have any idea why that prediction is being made. And of course, this is an active area of research. Fostering responsibility and accountability. So although AI technologies can perform specific tasks, it is the responsibility of the stakeholders to ensure that they can perform those tasks. And we saw that example with the coffee mug earlier. So this is crucial because it was a bit of a silly example, but you can see this being in the clinic where if an AI algorithm is used indiscriminately, it can lead to very, dire consequences. And it's really the responsibility of clinicians to ensure accountability in this case. Of course, we need to ensure inclusiveness and equity, and AI for health needs to be designed to encourage the widest possible appropriate, equitable use and access of the algorithm, and to promote AI that is responsive and sustainable. The FDA has also been doing a lot of work on this topic. They have the proposed regulatory framework for modification to AI algorithms and machine learning software as a medical device, and recently published an action plan based on this proposed protocol. And a lot of this is based on the idea of good machine learning practices and the idea of a total product life cycle. So that, at the top here in the white, you see this is basically what we were talking about during my presentation. So, preclinical use, using data selection and management, training a model, and validating this model. And then once you have a model that works well, in the bench, then you deploy it in an application, and then you use it with actual patients. But you need to assess the performance of this model and monitor it constantly. And what's also interesting with AI models is with time, there may be new data coming in. For example, with our device identification app, there may be new device coming in that may be different. And if we retrain the model, we have to make sure that it still performs to the same level as the initial model that was at regulatory approval, for example. So this is a very important aspect when we're looking at devices using AI techniques. So to summarize, we've spoken about basic concepts in AI, applications of AI in cardiac imaging. Again, a very brief overview, some examples of projects at the Heart Institute, and some challenges and ethical consideration. So it's a pleasure to present again today. And I want to thank my mentors and supervisors amongst the years, as well as my collaborators in the Heart Institute at MITRE, and the leadership of the Heart Institute. That's been really a pleasure to be working here.
Thank you, Pascal. That was excellent. If people have questions, please raise your hand and we will unmute your microphone. I apologize, my camera is not working this morning. I have a question. How do you envision this type of technology in an educational role? Do you think it's going to help or hinder skill development of unexperienced clinicians?
Yeah, it's a great point. And you can see it in different fields and it's not unique to AI. You can imagine any new technology that comes in can definitely have a big impact on how clinicians are being trained. I think AI in particular may take over some of the more rote tasks that are being performed, and really currently most of the AI algorithms that are in clinical use are more akin to a linear regression model, and they can make predictions that are useful and may help the clinical flow, but don't necessarily come up with a diagnosis on their own. So they still need very intense human input and to make sure that the predictions that are being made are reasonable. And of course, as trainees using some of these methods, I think we may shift the focus from more rote and kind of manually intensive and laborious aspects of of clinical work and shift it towards more efficient and patient-centered care, where that's where humans can really provide a big plus value. So, for example, with the MRI, example, if you spend hours and hours just outlining a ventricle or making manual measurements in an image, you're not adding that much plus value to the patient. If you can quickly review the images, I think that gives a lot of power to a human in the equation in this case.
I think Dr. Beanlands has a question.
Yeah, Pascal, this is awesome. Great presentation, and really informative. Maybe the black box is now a little bit gray for some of us, or more clear, as it were. I appreciate that, and really like the analogy with the coffee mug, your Medtronic coffee mug. So
yeah, exactly.
So that was cool. I guess a question I have is, again, along the lines of what Dr. Stadnik asked, and to me, that AI becomes another tool, that it doesn't necessarily replace, does not replace that what we do clinically with our patients, one-on-one, individualized, etc. And perhaps it's best used as a tool or an augmenting tool. Just like anything else, you don't necessarily rely 100% on a given test all the time. You use your best clinical judgment. And I guess my question to you is, have people looked at that interface and basically the so-called augmented human intelligence, using AI to basically work together with the clinical expert to better enhance care, enhance prediction of outcomes, et cetera, et cetera? It's not clear to me that that's actually been done.
Yeah, that's a fantastic question, actually, because I think if you're really looking at the how a patient goes through from diagnosis to treatment of a given condition, the AI algorithm may have impact at several points of this. And right now, what a lot of the research that's been done, it really looks at accuracy of the algorithm, but not necessarily at how it impacts outcomes. How well would it really help the diagnosis of a disease in a clinical trial, for example, or if it really helps, decrease the rates of a certain complication. So this is really, I think, the next step in this, and I think that the interaction of humans with AI algorithm is really key. For example, if you were to design a clinical trial for a predictive model, you add an extra complicating or confounding variable here, whether the human will believe what the AI algorithm provides in terms of a prediction, and whether the outcomes of the trial really are representative of what the device or the algorithm has produced as a prediction. So you add this extra confounder, and I think that this in the future will need to be studied. And of course, this is an expanding field and relatively new. So I think it's going to be, over the next few years, we'll see more studies going in that direction. I totally agree.
Dr. Masana has a question. Dr. Masana, if you could unmute your mic.
Yeah, you hear me?
Yes, we can.
Well, first of all, thank you, Ellie. So first of all, Pascal, this is one of the most outstanding talk I have and presentation I've seen at the Heart Institute for 20 years for two reasons. First, it was extremely well done. Second, it was extremely clear. I think it's the clearest presentation and explanation of AI I've ever seen. And third, because whether we like it or not, AI is the future of medicine. There is absolutely no doubt that in 25 years, we will not have the number of nurses and doctors that we need. And this is done. I mean, this is no question that AI is going to dominate medicine more and more. So this is a vision the Institute had already 2-3 years ago. And I thank you for actually doing all the work you have done. I've been invited to write a chapter on AI in cardiovascular medicine as a CEO, like they call it the view from the top, because they have realized that many cardiovascular centers have absolutely no vision in AI and have not invested in AI. And we have the opposite problem, it's not problem, but the opposite position is that we have invested heavily in AI. So thank you for using all the investments and benefiting the Institute and the research. And this is all aside from all what we do with Oracle research. So now the job of clinicians is really to understand all of that and try to ask questions. What is available for me? How can I get into this? Because there is a unique opportunity for clinicians at the Institute to be on the top of the game. And this is very important. So the more, I would say, you cannot afford to have like maybe 10 or 15 AI experts, but we need to have physicians understanding, and there is so many applications. So cardiac imaging is obviously something which is clear, but we have a lot more applications, like in terms of predicting of outcomes, in terms of triage of patient, in terms of even administrative tasks, like organizing OR schedules or cath lab schedules based on data collected from timing in the OR, from per physician, per patient, depending on the patient. And we can improve the function of the hospitals dramatically with AI. It's going to take years, but it will happen. And in 10, 15 years, you're going to see many more things AI-driven in a hospital. So I'm glad that you have taken the helm of that. Congratulations. You're a fantastic researcher, and I'm very impressed by the work that you do. And thank you for playing the game, if I may say.
Oh, that's very kind. I really appreciate that. It's very humbling. Thank you very much.
Okay, I think we'll come to an end. Pascal, again, thank you very much. That was a visionary presentation of the future. So we appreciate it, and it's a little more clear to me now how this works, as Dr. Beanlands alluded to. Next week will be a Grand Rounds event, so please look for the invitation from Research Services regarding that. You'll have to register for the Zoom presentation. Have a good week, and we'll see everyone next week.
Thanks again, Pascal. Great work, man.
Oh, thank you. That's very kind. Thank you so much.